Hello friends, welcome to another video from Field Academy where we learn together from each other. So today's topic is binary tree and we'll discuss a few types of binary trees and also some variants of binary trees. So let's get started. So this is what we are going to discuss in all. We'll first discuss what a binary tree is, then we will see what a full binary tree is, what a complete binary tree is, then we'll see what a perfect binary tree is. We'll also see what a balanced binary tree is. Then we'll move to a variant of binary tree or a special kind of binary tree, which is binary search tree. We'll see two types of binary search trees which have some great applications in computing, AVL tree and red-black tree, and at last we'll end with a generalization of binary search tree which is a BTree. So let's move ahead. So what is a binary tree? So we have already seen what a tree is or what a tree data structure is. So binary tree is a special kind of a tree where every node or every node has at max 2 children. It might have 1 children, it might have 2, or it may not have any children. And sometimes we also call them as a left child or a right child. So here we can see an example of a binary tree which has a root at 2, and we have few more nodes here which are 7, 2, 6, 5, 11, 5, 9 and 4. So coming back to the definition again, if you see any node, let's say we take 5, it has a left child or a right child. So in this case it has a right child, it doesn't have a left child. Similarly, node 6 has a left child and a right child. Left child is 5, right child is 11. So what is a node? First of all, a node is a primary composition, or a node is a primary element in a binary tree. So it's like vertices in graphs which are connected through edges. So an example could be node 6, which we have taken as an example. Then every binary tree has a root which is the topmost node. So in this case our topmost node is 2. Then we also have child or children, we call left child, right child. So a node basically child is a node which is at a lower level than the current node. An example is child 5. 5 is a child of node 6. Then similarly the concept of parent is a node which is at higher level. So in the tree here 7 is the parent node of node 6. Then what a leaf is nothing but a node in the lowest most level which doesn't have any children, which means it doesn't have any left child or a right child. Some examples are 2, 5, 11, 4. They are all leaves. Then comes depth of a node. So depth of a node is the distance from the root, which means some total number of edges from the root to the node. So if we have to compute the depth of node 6, then it would be 2, because there are 2 edges, 2, 7 and 7, 6, through which we can reach node 6 from the root 2. Now a depth of a binary tree or the entire binary tree is nothing but the distance from the root to the farthest leaf, which means the leaf that is located as far as possible. So in this case, if we see 2 as the root node, and the farthest nodes could be 5, 11 or 4, and in each case if we notice there are the total sum is basically 4, which means we can go from edge 2 to node 2 to node 5, 5 to 9, 9 to 4. We also sometimes call the depth of a binary tree as height of the binary tree. So in this case the height of the binary tree is 3. Now let's move on to see some types of binary trees. We'll see what a full binary tree is. So full binary tree is a special kind of binary tree that has either 0 children or no children. So which means there cannot be nodes that have one child. So here is an example of binary tree. If you notice, all the nodes here have either 2 children or no children. Then a complete binary tree. So complete binary tree is a tree where at every levels the nodes are completely full except at the last level where it might not have all the nodes. So here we can see complete binary tree. This one has all the nodes in all levels. In this case it has all the nodes in 3 levels, but the last level only has 3 nodes. So this is what a complete binary tree is. Then moving on to the concept of perfect binary tree. So perfect binary tree is a binary tree in which strictly all internal nodes have 2 children. So there cannot be any internal node with no children or 1 children. Then a balanced binary tree. A balanced binary tree is another specific kind of binary tree where the height of the left subtree and the right subtree can only differ by 1. So this kind of binary tree has a great applications for searching and other purposes, because searching, inserting and deletion is in logarithmic time. So if you notice the balanced binary tree here, the left subtree has height 3, 1, 2 and 3, whereas the right subtree has height 2. So this is a balanced tree. If it was another level over here, then it wouldn't be balanced anymore. So now a special kind of binary tree is a binary search tree where an important property is present. So the important property that is present in a binary search tree is that every node every node has its children, has its left subtree smaller than itself and right subtree as bigger than itself. So which means if we take a node, let's say we take the node 8, all nodes to left of it are smaller than 8 and all nodes to right of it are greater than 8, and this property applies to every node in the binary tree. If we take 6, the same property applies. 4 is less than 6 and 7 is greater than 6. So this is a very important kind of tree where certain operations like search, insert and delete all can be done in order log n time, which is just proportional to its height. So you can see if we compare it to a normal array data structure, this can be a great benefit for us. In fact, if a binary search tree is unbalanced, operations might still become costlier. Why? Because let's say we have a binary tree, something like this, where we only have right child, then searching or finding is similar to an array, which means it again costs us linear time. Let's say we have nodes 1, 2, 3 and 4. Now in such a binary tree is unbalanced and operations are still costlier and no longer logarithmic. But still, binary search tree is the most simple data structure or commonly used data structure we use for searching. So moving on, we have a special kind of binary search tree which is a balanced binary tree, which means the difference in height between left subtree and right subtree of any node at max differs by 1. So this was invented by 3 researchers and and this tree has a property that even in the worst case, search, deletion and insertion all can be done in order and time. In fact, if during insertion or deletion, if the property or the balance property gets violated, we we can rebalance the tree using tree rotations. So in this tree, every node maintains a balance factor which varies between -1 to 1, just to indicate the difference between or its left subtree and right subtree. So great, let's move ahead to another kind of balanced binary search tree. So it's a red black tree. So interesting, isn't it? Now nodes have colors. So this is a binary subtree where nodes have colors, either red or black, and this color property helps determining whether you know um, basically helps in balancing the subtree whenever it gets balanced. In fact, in this tree, whenever the balancing property is violated, we can rebalance using tree rotations, as well as sometimes even recoloring might be needed. So we won't go into details into what this is, but it's good to know that such trees are present where searching as well as searching, deletion and insertion all are in logarithmic time, even in worst case. So moving on to the last one, which is BTree. Now this is not a binary search tree, it's a generalization of a binary search tree. So it's not even a binary tree, in fact. So this is a tree where nodes can have more than 2 children and nodes can have more than 2 keys. In fact, we say for a BTree of order m, every node or every internal node will have minimum of m by 2 children and maximum of m children, and also the tree is balanced. So this is also a tree where searches, insertion and deletion are in order n time. So the concept of BTree has evolved from binary search tree only, where binary search tree had 2 children as well as the data inside it was sorted, which means it was organized in such a way that left side has smaller keys than the node and right subtree had higher keys than the node. So the same concept here applies, where actually the the subtrees fall in different partitions of ranges. So in this case, if we take 7 as a node, all its children are from 1 to 6, less than 6, and anything in between 7 to 16 is stored in the second node, which is 9 to 12. So this is used in databases and file systems for doing search and others for searching. So cool. Looks like we are already done with binary trees and its variants. So let's come back to final slide, which is the review questions. So here are some questions for a review. We have given a tree on the right side. So first question, what can we say about the depth of a perfect binary tree? Second, if a binary tree has n nodes, what would be the height of a complete binary tree? Third, is the given binary tree on the right a binary search tree? Why or why not? Please explain. Last question, which type of tree maintains a color attribute to balance itself? Alright, post your comments and answers to these review questions and I'll definitely look at it. Thanks again for watching another video, and I encourage you to watch other videos on my channel, and please share, like and subscribe if you like it. Alright, thanks guys, bye.